All right, you guys. This is very similar to some of the word problems we've done in the past. There's a little extra kind of bump in the road that we have to talk about that we haven't done before. We have to compare something with an E in it to the actual rate of change, and I'll show you how to do that. I didn't bring my graphing calculator, but I will talk about what to do, right? So if you look at this, this says solve each problem using the graphing calculator, right? And then determine the growth rate or decay rate of function. Dow Jones Index is stock market index for the New York Stock Exchange. The Dow Jones Index for the period, 20 years, from 1980 to 2000, was modeled by this formula. So we have V, DJ, which is Dow Jones, right? T is equal to 878, that's a start amount. E to the growth is 0.121 T. So it grows at a little over 12% in terms of years, and it started at 871. That's an amazing amount. This is a great time to invest. What T is the number of years after 1980. Determine how many years after the Dow Jones reached 3,000. So I'm just going to say f of x equals 3,000. Now, I'm going to talk about a couple things. All you've got to do is put that in your calculator. Put this in your calculator. Know that your x values, min and max, are from 1 to 20. Right? Your y values have to go up to at least 3,000, maybe a little higher so you can see it well, and graph it and find out where they cross. We have done these, so I feel less guilty about not doing one right now because I didn't bring a calculator home. And if you do that, you should try that on your calculator, at least one or two of these, and find out that they cross about these points, about 10.2 years. And I want to show you one more thing. All right? They say determine the growth rate. This is a growth rate. And I'm going to circle the portion. This portion right here indicates your growth rate. So if I set it up, e to the 1.121 is actually equal to 1 plus your growth rate, because this is your growth rate. All right. If I wrote the other one right, A, that's our start. And we have 1 plus r to the t power. That's how we did exponential growth on the other one. Look, there's my A right here and here. There's my t right here and here. Whatever is left equals my growth rate. Alright. So if I subtract 1, I get rate is equal to the E 0.121 minus 1, and you put that in your calculator and you get a growth rate of about 13%. Even though this is about 12%, because it's compounding continuous, it turns into about 13%. Alright, I'm going to write that. So let's look again. We can talk about this tomorrow. Talk to me if you don't understand this, because there's going to be questions like this, and I would love to go through them. It's really a lot easier once you see a few. There's not a lot happening, right? So same concept here. We've got this formula. So nickel 225 index, stock market index for Tokyo Stock Exchange, right? For 1990 to 2010 can be modeled like this. And do you see that negative up there? That means there's a decay. This stock market dropped. All right. Where T is the number of years after 1990. Determine how many years after 1990 it reached 15,000. Notice it started at 23,000. A good indication also that it dropped. So you can see, hey, my end rate's lower than my start rate, and I also got a negative up here. So if I set this up, right, we've got V, I'm just going to say V of T. I'm going to, and this is just kind of a label for the stock exchange that it's talking about, equals 23-500 e to the negative 0.0381 t. It's going down very slowly, but it is going down. And then I'd have g of x, I should have put a t over here and I didn't, equals, well, about 15,000. And again, if you graph both of these, graph this and this, you're going to notice a slow decline, and it will equate to this value in about 11.3 years. Alright. Now once again, I'm going to circle it. Remember, that's our start, that's the time. Whatever's left, this is equal to decay. E to the negative 0.038 is equal to decay, and remember, now it's going to be 1 minus the ratio because we're decaying, right? We're not growing, we're decaying. So 100% minus our decay rate will give us how much is left remaining right there. And, well, what do we do with this? We subtract 1. And if I do that, I got e to the negative 0.038 minus 1 equals negative r. Then we multiply by a negative 1. So on this side, that'll make that a positive r. If I multiply this side by a negative 1, let's write it in. It makes everything over here opposite. So that gives me a positive 1 and a negative e to the negative 0.038. If you plug that in your calculator, you're going to get a decay rate of about 3.7%. Remember, that is decay rate. All right. Paleontologists, once again, we got just something to plug in your calculator. Uncovers a saber-toothed tiger in California. Analyzes and concludes the specimen has 15% of its original carbon-14. We can talk about what carbon-14 is, that radioactive element. The percent of the original carbon-14 in the specimen after T years can be modeled by this. So we know N of T is equal to, starts at 100%, e to the decay, it's 0.00012 T. And this could be a huge number, by the way. We're talking about dead cats from thousands and thousands and thousands of years ago. So when you set your Y value on something like this, you're going to have a lot. Actually, when you set your X value, forget the Y value because X is time. We're going back in time. You're going to have a huge window. And we want to find out where N of T, so I'll just say F of X is equal to 15%, a very slow growth rate. I'm going to give you the answer, right? My time, if you graph this, look, my actual answer is going to be 15,800 years old. Once again, I'm going to circle this part right here. Boom, boom, boom. I'm going to set e to the negative 0.0012 t equal to, well, we got 1 minus our growth rate. Subtract 1, divide by negative 1. You get r is equal to 1 minus e to the negative 0.0012 power. I should have put the t in there over here. I did. And your growth rate is going to be approximately 0.012%. That means I'm moving the decimal over 2 more spots. A very slow decay rate right there. We have talked about all this before. Transformation, the change in end behavior. Right, that's going to be A, and that's it. That's the only one that changes end behavior. Right, transformation to change the y-intercept. That's all of the transformations. And how can this right here be used in exponential growth or as decay? Well, if C is positive, it's growth. Right, this part right here, if C is negative, it's decay. And this is it. We can talk about more. Oh, let me actually show what I wrote right there. C is positive is growth. C is negative is decay. Again, most of this is just plugging into the calculator. I'll try to do one of these for you tomorrow in class, but get this down, and I'll see you soon.